Hi there, and welcome back to Triplicate. And today we're going to move on with the mean green synthesizer. And last time we got all the controls wired up and working. And on the last synthesizer tutorial we got enough synthesizer elements created and written to make a basic synthesizer which sounds like this. So in this video I want to take a MIDI keyboard, a MIDI lead, and be able to play that synthesizer sound from a MIDI keyboard. None of the controls will work, won't be editable or anything. It would just be really nice to get to the point of actually having something that'll play notes. Okay, so I have off camera taken the files from the development version of the synthesizer we developed on the last synthesis tutorial video. So we now have an envelope.c, a filter.c, a MIDI.c, which I'll come to in a minute, an oscillator.c, a parameter.c, and a voice.c. And I've done the fiddling needed to make those compile and converted them from C++. Now, to play notes we need to get notes in, so let's look at MIDI.c. We have a do MIDI in function which is called every time the main loop goes round, and while there is MIDI input bytes to read, it checks to see if there are a status byte and sets the mode accordingly. Now we're only interested with note on and note off so far, so just ignores the rest. And if it's not a status byte, it's looking for either the first data byte or the second data byte, and when it's got the second data byte it goes to look for the first data byte again to implement running status, and when it's got a second data byte it displays note off, as you'll see in a minute. That's just for debugging. And if the currently playing voice note is the same as the note it's got in on the note off message, it calls the note off. This will be a more sophisticated implementation of note handling eventually, but this will do for now. And similarly the note on, if the velocity is 0 it does the note off thing again, otherwise it turns the note on. Very simple. So shall we see what it does? Okay, we've uploaded the code, so shall we start it? Off she goes, and should we play some notes on the keyboard? Well, there she goes. Happy with that? Okay, let's move on and see if we can get the synthesizer part working. Okay, so I've done quite a lot of debugging, and rather than having you looking at me going for hours, I shall just bring you up to date with where I am. So here we go. I've changed the do synth audio function, which calculates one buffer, from the one that I was using that did 2 triangle waves for testing, to this one which calls voice do, which is the main synthesizer voice function. And I've got them code switchable so I can always go back and get it to do the triangle waves as a sanity check. So I fired this up and it was absolutely stone dead. Nothing happened. Until I realised that the PC version we had that little sequencer which was feeding values into the synthesizer, whereas in this case the whole of all the values in the synthesizer were 0 and it wouldn't do an awful lot. So I invented a little function here which just set all the values up to some default values. So while I was investigating the complete lack of output problem, I actually changed it here, commented the mixer, one of the oscillators and the filter out, so it's just outputting oscillator 1 and nothing else, just as a sanity check. So having got that far, I got a noise out of it, and that noise sounded like this. Okay, let's fire her up. And that does not sound good, but so it's sort of doing something in response to the keyboard, but it's also making a horrible noise. So now let's have a look into that. Okay, so as you can see, I have one scope probe on one channel of the output. It's just outputting the same to both channels at the minute, and the other one on a port pin, just so we can use the port pin for debugging purposes. So let's see what that produces. Okay, so in the do synth audio function where it calculates one buffer's worth of samples, the start of this calculation process I've set that pin high, and at the end I've set it low. So we get a signal every buffer calculation, we know how long the buffer takes to calculate. So I've also turned the audio off because it makes a nasty noise. So should we fire that up? Right, we're ready to rock, so we'll start her up and go and look at the picoscope. So that's 1 millisecond division, and each one of these we can see is taking right 0.88, nearly 0.9, and that's where our horrible noise is coming from. It doesn't seem to be calculating the buffers reliably, and 0.99 of a millisecond to calculate those samples. It's far too long. Okay, for test purposes, let's go back and put the test triangle wave back in. Okay, let's fire it up. I'll just connect the speakers up again. So yeah, you can hear it, see it's making our triangle wave nicely. So what are we getting on the picoscope? We're getting a triangle wave, and it's not taking very long to calculate them. Also, interestingly, it calculates a new buffer every 2/3 of a millisecond. So as it was taking longer to calculate a buffer than it had to do it in before the buffer needed to be out there and on to the next one. So we have some crazy problem with the code taking way too long, way too long. So the next job is to have a look at that. Okay, so I've gone back into Voice Do, and here is one parameter update for the voice pitch, and I've put my GPIO pin to go up at the start and down at the end. So shall we see how long that takes, bearing in mind there are quite a few of those to do per voice. Okay, there we go, and it's now producing 32 I think pulses per buffer calculation. So we need to go into here at 5 microseconds. which is far too long. Bearing in mind, each sample has to be calculated in a maximum of 20 microseconds, and if we want 20 note polyphony, then that's 1 microsecond per voice. So for a start, here we have a problem we need to look into. So should we look at that? And if we go into parameter.h, we suddenly know that the smoothing calculation for the parameter output is still being done in floating point, so that'll slow it down. So should we get rid of that floating point, do that in integer arithmetic, and see if that helps. Okay, so here we go. I've changed all the smoothing filter variables to be integers, and I've changed the code to all these integers. So let's see how much improvement that gets us. Okay, so we'll run it up, go to the scope, and there we go. That's 1 microsecond division, so that's 1 microsecond and a bit, which is still way too much. So I am going to do some digging and find out what's going wrong, and just run the synthesizer code round in a loop. So I'm taking all this, whatever's happening here, with some interrupt, so I can just measure how long the code's taking. So I will do that, do some digging, and bring you back. Okay, the joys of writing software, especially embedded software. So just to further test the timings, I put these 2 lines in either side of the call to do the synthesizer audio, just to see how long that would take. And when I fired it up, this happens. The hard fault handler, it's gone into the hard fault handler. And I added this return in so I could step on and find out where the hard fault occurred. It occurred there, which seems like a crazy place. How can adding one to the system clock cause a hard fault? So I went back. I assumed it was in somewhere in the do synth audio, and went back and hunted through and ended up in the oscillator function, just commenting code out and trying it and saying, oh, that works, and putting code back in and that doesn't work, and found out if I took these functions and replaced the multiply with addition, it would be fine. So it's one of those crazy things where you think, there's no logic, this is weird, which experience tells me is some kind of a memory problem. I'm writing something, say usually beyond the end of an array, and it's upsetting some memory that has some consequences somewhere else. So I looked around on this basis, and I found somewhere, where are we? This little howler. Voice do, you pass a pointer to a buffer, but it expects that buffer to be 2 words long for stereo, because eventually the voice will have a panner on the end. However, here I have only passed it a 1-word buffer, so it's writing one of the words be outside the local storage for this function, and as a result upsetting the stack, which generally causes all sorts of weird things to happen. So all we need to do now is make that an array of 2, and the array name is a pointer. Make those the 2 members of the array, fire it down, And we're ready to go. Fire it up, look on the scope, and that's fine, that's running. What's more, it's not taking too long, and for running into the next period time it should be calculating the next samples, so that was something to do with that. Okay, and here it is with the audio connected up and the keyboard going. So there we can see we have a sawtooth wave, which you can change the frequency with the keyboard, and it's noisy because of this, the scope earthing is causing the noise, not the waveform. So one easy way of getting extra performance out is switching from debug mode to release mode in the code. And if we go back into the editor, we do have, in the run menu, we have a debug, which is what I've been using, and a run. And I sort of fought that and fought that, and it didn't seem to want to. Well, I tried it in run mode, it seemed to complain and produce errors when it was trying to upload the code. But a little digging told me that this is actually, this editor is for, you know, general purpose use. You can use it with sort of all sorts of chips. But the Nucleo boards, they're only really ever in debug mode. So to get into run mode, we have to go into debug configurations, and you can see here the mean green debug one is made for you when you set up the project, but the mean green run one is a copy of that. However, I have sort of made some changes, so it now goes in, it now looks for the release ELF sort of output file as opposed to the debug, which looks for the debug. Okay, and it automatically builds the release when you hit F11. And if we look in the project properties under C++ build, so it says release is active. Oh, we're looking here, that's its settings. Well, we have optimization and debugging, so we are in release debugging level none. So we're doing no debugging at all, so any debugging stuff it puts in the code we're not doing. And optimization we have set to optimize most, whereas for the debug it's optimized for debug. Okay, so let us first try it in debug. We're in debug. Let's see what happens. And it's running mean green main debug, so we're gonna get that. There we go, it's ready to go. And we go into the scope. Let's have this at 200 milliseconds of division, so 450 milliseconds it takes to run. So we are now going to go back into our editor. We're going to stop it. We are going to say run. We're going to have debug configurations, run, and we're going to run that one. Okay, you see here the code, source code, is now no longer in the assembler, which is a good sign in terms of it producing release code. So shall we see what it does now? Shall we fire it up? Go back into the scope. So it's going again, and that is 200, 300 and... oh, hang on. If I do that, it'll tell us 320 or thereabouts microseconds. So a quick calculation: 320 divided by 450 equals 71%. So it's going to get us a third, I guess. So it's not really going to help that much. So it's back into trying to find why the code is taking so long. Okay, so we want to try and make the code run faster. Quite a lot faster, as it happens. So we need to look at each bit in turn, and we're going to start by looking at the parameter update function, because it's called in a few places, so any savings in that are multiplied. So to start with, we've got the LED pin, which lights the little LED on the Nucleo board. It goes high before the function's called and low after the function's finished. So shall we see what happens with that? I'll go to the beaker scope. There we go, that's it. Now that's all very well, but that is jittering about quite badly, which is going to make it hard to use. And after a bit of digging, I discovered that is because the A to D converter interrupt is being called when it finishes reading one bank of pots and moves on to the next. So this bottom trace is now another port output, so we can monitor the timings of 2 points at once. So let us go to the A to D conversion interrupt routine, which is this, and set that line going. Yep, so there we can see that is appearing in the middle of the parameter update function on occasions. So what I've done is create an ADC active variable, which is just used for testing, which is set to 1 as the analog to digital sequence runs through. And if we go back to here, we will only actually look at what's going on in the parameter update when the analog to digital isn't running, and that'll get rid of the jitter like this. Okay, so here you can see now the bottom trace is not happening and the top trace is stable, so we're only looking at the ones that are not getting interrupted. And you can also see that that is about, well, let me put this, 1 1/4 microseconds long, which is longer than we want. So what is it in the parameter update that's taking so much time? Okay, so here we are in the parameter update function, and we've set our second test pin high before it goes into the smoothing function and low after it comes out, so we can see how much of the parameter update, the time of the parameter update function, is taken in the smoothing function. So shall we give that a whirl? Okay, so here we are, and you can see that the bottom trace is over half the time in the parameter update, so that's the smoothing function. So I think we need to look at that smoothing function and see if we can make that go quite a lot quicker. Okay, so let us put a breakpoint where it calls the smooth function, and we'll just step through the code and count the instructions and see which particular bits are taking a long time. Off we go. Yep. Right, so here we have disassembly. Now I am not hoping, well, I am not planning on getting into ARM assembler unless I absolutely have to. However, it does let us count the instructions and give us a feel for where things are going slowly. Right, so instruction setting, stepping mode we want on. So should we count? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 50, 51, 50, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76. Okay, but as you probably noticed, it calls the mult function 3 times. There we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 for the mult function. It's called 3 times, so that's 48 out of 76. So 3/4, 3/5 maybe of the steps for that smooth resonant filter function are in the mult function. And here is the mult function we were using, which is the one we wrote for the PC, and as you can see, it casts everything to 64 bits, does the calculation at 64 bits, and then just converts the result back. So let us see if we can come up with a version of this which is more efficient. Okay, so this is our test multiply function. Basically goes round and round and round and round doing a multiply and changing the values, and every 32,000 and some it just flips the test line so we can measure how long it's taking. So first up, we want to know how much the overhead is involved in just doing this, maintaining this loop. So we've got no multiply in at that, and if we run that, we get 7.325, 7.33 for the loop only. That's just the overhead to run this loop, which I've noted there. Now if we put simple multiplying, which won't do us because when the numbers get too big it will overload. We get 8.925. so if we go back into here, there, I've already tested these and recorded them. Okay, that will give a time of about 1.6 milliseconds for multiply. Okay, so now let's try it on our function as we now have it, as we're calling it, so which is that one. So recompile and off we go. Fire it up, have a look. Oh, that's a lot. So that is 14.29. So if we go back into here, 14.29 gives us 6.94 milliseconds, nearly 7 milliseconds for the multiply, which is 4 times as much. So we can certainly lose some, I think. So there's certainly room for improvement. Now, after playing around, and I'll show you it in a minute, I came up with what I've called Mult Fast 64. And shall we try this? Here we go. Which is 9.32 or so, which if we calculate it out gives a time of 1.96 against 1.6 for the straight multiply. So that's not too bad at all. And shall we have a quick look at my routine? Well, here it is, and I did look online and do quite a bit of googling, and this came out as being the best way of doing it is put the SML instruction in assembler, and that's how you do it. I don't profess to know the ins and outs of that. I've just copied it out of somebody else's post, and at the end here I'm shifting it by 16. So okay, we can make our multiply go a lot faster. So things are looking up. Okay, so it's embarrassment time. Right, who reads data sheets? Unless you have to. You get to the point where you need to know how to set something up, so you look in the data sheet. And I chose this particular chip, this particular Nucleo, because it was the one that went at 180 megahertz, which we need as much processing as possible for a synthesizer. But while I was actually looking at the data sheet and trying to work out how to make things a bit faster, I spotted the embarrassing fact. Can you see it? Yes, this processor has a floating point unit in it, so we could actually do our calculations in floating point. And after I've banged on about using floating point wherever possible in the synthesis tutorials, I sort of think maybe we should go over to floating point. So in the meantime, let's just test our multiplication routine using the floating point instructions. Okay, so here we have a version of the function we looked at just now, called test float multiply, which does the same thing. It takes two floating point numbers and changes them every time round the loop, and every 32,000 and some it flips the output pin so we can measure the speed. So shall we do the baseline measurement with no multiplication in? There we go. Start it up. Measure the time is 7.325. So I've already done this and recorded it there. So now shall we put our floating point calculation back in and run it again, compile it and upload it and run it. Right, there we go, fire it up, and it is now 8.946. and if we subtract 7.35 from that, we get 1.6 milliseconds for the multiply. And if we look back at our best integer version, that was 1.96. So we can do floating point faster than integer. Okay, so I think I'm gonna call a halt to this video at this point. I know we wanted to try and get our basic voice working, but I need to make a decision. Are we going to press on using integer arithmetic, since we've done quite a lot of work at that, or are we going to go straight over and start using the floating point now, which will take a lot of conversion, and I will go back into the PC code and debug it in there. So we haven't got to where we wanted to, but that's development for you. The boss says, you know, where is it? You said it'd take 2 months, and 4 months later I'm still scratching my head. That's how it goes. So I'm sure next video in this series we'll get her to make a proper synthesizer type noise. But for now I'm going to call it a day. So subscribe, comment, thumbs up. I know it's been a long video and a lot of software, which isn't the most exciting. So for now it's goodbye from Triplicate, home of interesting electronics. Goodbye.